Hi guys, in this video we're going to start with chapter 2.5 on Cartesian vectors. Cartesian vectors, you were introduced to Cartesian vectors previously, but mainly in the two dimensions. And perhaps the best way to start is by reading this opening sentence, which I feel is very helpful. It says, the operations of vector algebra, okay, let's just stop there. The operations of vector algebra, what does that mean? That means when we are adding and subtracting and multiplying vectors, right? Operations of vector algebra. So the operations of vector algebra, when applied to solving problems in 3 dimensions, okay, are greatly simplified if the vectors are first represented in Cartesian vector form. Okay, so that really is the main idea here, is that, remember in chapter 2.4 you were resolving problems into their x and y components in order to calculate resultant forces in the x direction, resultant forces in the y direction, and then you got your overall resultant force. Do you recall in chapter 2.4 that you carried out these operations in scalar form and in Cartesian vector form? And do you recall which was slightly simpler? Well, in 2 dimensions, it is slightly easier just to carry out those calculations or operations in scalar form, meaning you don't need to initially convert the force vectors into Cartesian vector form. You just need to obtain the components in the x and y direction and then find the resultant. But it was a good exercise to practice converting those forces into Cartesian vector form, because when we get to 3 dimensions, when there is now not only an x and a y component but a z component, then it becomes a lot easier when we convert the force vectors into Cartesian vector form. Okay, so that is the basic idea that I want to impress upon you, is that in 3 dimensions, it is really very important for us to convert the forces into Cartesian vector form. Okay, and we will go through that as we go along in this video and then the next video. Okay. So just to go over this quickly, we use a right-handed coordinate system. That simply means that that is our z direction, that's our x direction, and that's our y. If you recall, in 2 dimensions, often we represent it in this way, x and y, and then z would be coming out of the page. Okay, so if that's your x, which is x, and that's your y, remember these are all right angles. Okay, just like these are right angles. So x and y, this is in 2 dimensions, and this is in 3 dimensions. Okay, don't want to spend too much time on that. Just quickly recapping. Again, if we have our x, y, and z axes, and we have a vector here, vector A, right? Then in 3 dimensions, this vector A, I'm going to put a little bar over it, is made up of 3 components: a x plus a y plus a z. Okay, now please take note, this is in vector form, but this is not in Cartesian vector form. All we're saying is that the vector A is equal to the addition of vector A, the x component of A plus the y component of A plus the z component. So if we draw that down, say like that, and we draw that like that, we will see that then refers to our ax vector, that refers to ay, and then that we're also, again, we need to make use of the parallelogram method. That then is our AZ component. So do you see that that A vector, resultant vector, is equal to AX plus AY plus AZ. Another way of looking at it is, if I walk this in the X direction, if I walk in the X direction, that magnitude, and I walk in the Y direction, right, with that magnitude, and I walk in the Z direction with that magnitude, I end up at the tip of that vector. Okay. So please take note of that. This is just simply vector notation, but in the textbook it moves on to something called Cartesian vector notation, or rather even representation. Okay? So if you recall, in the previous videos, we spoke about I's, J's, and K's. Now what are these? These are unit vectors in the X, Y, and Z directions. They are simply vectors giving us a direction. So I is in the X direction, J is in the Y direction, and K is in the Z direction. They have a magnitude of 1. What does that mean? It means that if we have a vector here, say, let's call it F, equal to 10I Newton, then 10 refers to the magnitude of that vector, and then I simply gives it a direction. If we just say F is equal to 10 Newton, then we know what the magnitude is, but we don't know what the direction is. So if we say 10I, it means that we have 10 newtons in the I direction. I is a vector also with a magnitude and a direction. The direction is the x-axis and the magnitude is 1. So what happens is, if we multiply 10 by the unit vector I, we are essentially saying 10 times 1 in terms of the magnitude. Okay? So by multiplying by I, we are not changing the magnitude. We are simply giving that magnitude a direction. Okay? And really, again, this is Cartesian vector representation. Whereas here, we were just representing the x component of A by AX. Here we are representing the forces in Cartesian vector notation. Okay, so let's rewrite this in Cartesian vector notation. We can say A vector is equal to AX in the I direction plus AY in the J direction plus AZ in the K direction. Okay, so these are magnitudes in the X, Y, and Z direction. Could be 10, 20, anything, and then the I's, J's, and K's simply give these directions. So remember that we are adding up vectors here, vector addition. That vector plus that vector plus that vector gives us this resultant vector A. Okay? And then lastly, which I want to touch on before ending, is you should know that what is the magnitude of this vector A? Say the magnitude of A is simply A. Right, now I'm taking off that bar because now we're working with the magnitude, right? So it's no longer in vector form. And what do? We take AX, we square it, we add AY, the magnitudes, and we take AZ and we square that, and then we square root the total. Okay, so that then is your magnitude. Okay, so I think that's good for now. I didn't want to make this video too long. In the next one, we'll carry on with coordinate direction angles. Thank you.